In the previous video, we looked at how to take a curve and compute the length of that curve from one point to another using integrals. In this video, we're going to look at the idea of arc length from a slightly different perspective, and we're going to develop something that is called the arc length parameter. Right? Now, typically when we have been doing vector functions, we have been using the variable t as a parameter for the vector, since t often will represent time, and in most applications, a vector function is used to describe the position of an object over time. And so t is a very natural parameter or symbol to use for that variable. In this case, for some applications, particularly geometric ones that we might deal with later on, it's going to be useful to reparameterize the curve in terms of arc length. And this is where the arc length parameter is going to come into play. And so to develop the arc length parameter, we need to do a couple of things. The first thing that we need to do is we need to choose a base point for the parameter. And that can be any point on the curve. All right, we just need to give it a name. So I'm going to give it the name r of t naught. And like I said, it can be any point on C. So I'm going to pick this point right here that I'm identifying on the curve. And this will be r of t naught. So this will be my base point. And now all these other calculations that we do will be based on this point as our starting point. Right? So if we think about what a parameter does, this value of t in r of t that gives us this curve, in the simplest sort of breakdown of it, is that each value of t determines two things. Right? It determines a point on C, and once we have a point on C, it also determines a distance from my base point that I chose. All right, so once I pick any other point t, or r of t on this curve, then we can compute the arc length of that. And so that distance is a function of the value of t. And so what we're going to do is we're going to define it really symbolically as a function of t. So I'm going to define the arc length parameter to be s, and it is a function of t. And s of t is simply going to be the distance from r of t naught to r of t. So to do that, I just use the arc length integral that we just developed. So it's going to be the integral from t naught to t of the magnitude of r prime of u du. Right, now I'm using u here as the variable in the integration simply to avoid any confusion with having t mean different things. So u is simply a dummy variable for integration, so it won't have any really role other than that. What this integral does, if you just look at it, it says it's literally computing the arc length from r of t naught, the base point, to r of t. And of course, you could pick t to be anything that you want. But s of t is the distance from r of t naught to r of t. Now, a couple of things that we can see just from the definition of this integral. So if t is bigger than t naught, so if we pick the point r of t that's in the positive direction along C, then of course s of t will be positive. Because we're going in the positive direction. However, if t is less than t naught, then even though we're integrating something positive, we're going to basically be integrating backwards, and we know that backwards integration will result in a negative value. So even though s of t is giving us a distance, if we choose the points in the wrong order, if we choose a value of t behind r of t naught, this is going to give us a negative value. So it's really not the case that it's computing the distance. It's really computing a signed distance. It's telling you the distance from the base point, but also the direction from the base point. Is the point this number of units in the positive direction or the negative direction of our base point? So our key observation, right, that makes this number s a useful thing to do or to use is that for each value of s, we get a point which we'll call r of s on the curve. In other words, s turns out to be a parameter. For C. Right, so we're not going to get too much into the details about what a parameter is, but it's simply a variable that when you substitute a value in for that variable, you get a point in your bigger function. So in this particular case, if we have r of t, each value of t determines a point on the curve, so t is a parameter. But what we can also see here is that r of s, if we pick any value of s, we're going to get a parameter, or we're going to get another point on the curve, and that makes this a parameter as well. So with this parameterization given by the arc length s, the point r of t naught now becomes the point corresponding to s equals 0. It's the point 0 units away from our base point. If we then travel around in the positive direction, I go out, say, 1 unit in the positive direction, this will be the point given by s equal 1. If I go out 1 more unit in the positive direction, this will be the point given by s equal 2. And so this will be s equals 3 and s equals 4. And we could keep going if we wanted. But the nice thing about this is we know automatically that these blue points are all spaced exactly 1 unit apart in terms of the arc length of the curve. Now we can also describe points behind r of t naught, that base point that we picked. So this would be s is negative 1. And going back 1 more, we get s is negative 2. Right? And so here we see that every point on the curve is given by some s value. It's literally the distance from our base point to that curve. And so what we can do is we can reparameterize this curve. We can define everything in terms of s instead of in terms of t. And for some geometric properties that we're going to discuss in the future, this is extremely convenient to do. So we do want to give a formal definition for the arc length parameter that we just developed. So we'll do this really quickly. So the arc length parameter, s of t, is defined by the following integral. So s of t is equal to the integral from our base point t given by t naught to t of the square root of dx du squared plus dy du squared plus dz du squared du. Right, where again, u is just a dummy variable that's introduced to be different than the letter t. Before we do an example involving this, I want to point out one thing that we're going to need later on in the course. And that is, since I have this definition, and I'm just going to rewrite it in terms of the magnitude of the derivative like we did originally. So since s of t is defined this way, by the fundamental theorem of calculus, we have the following. Now remember, if you remember the fundamental theorem, there's actually 2 parts. There's the part that's the most useful in that you are able to evaluate an integral by finding an antiderivative plugging in the endpoints and subtracting. I'm actually talking about the other part where we have a function defined as an integral like we do in this case, and we want to differentiate it. That part of the fundamental theorem says that if I have this function s of t and I want to compute its derivative, because the lower limit is a constant, t naught, remember we picked t naught as just a fixed value so that we have a base point, and that the top value is a variable like t, the derivative of such a function is just the integrand function with t instead of u. And so s prime of t is going to be r prime of, or the magnitude of r prime of t. Right? So we're going to need this fact later, and it's just an application of the first fundamental theorem. And so just kind of keep this in the back of your mind, and when at some point when we say, remember when we mentioned this, think back to this particular item. So let's look at an example now where we actually have to reparameterize a curve with the arc length parameter. All right, so we're going to look at the vector valued function r of t equals cosine t, t over 2, and sine of t with respect to arc length. Right? So we are given this vector function in terms of a parameter t, and we want to reparameterize it. So we want to find a function r of s, which will sketch out the exact same curve as this particular function here does. So the first thing that we need to do this is we need to pick a base point. And we can pick any point that we want for this. It will give us a slightly different answer if you pick something different, but it will the parameterization will be different, but the curve will be the same. And so typically what we're going to do for the base point, unless there's a more natural option, is we're just going to pick r of 0 to be the base point. This is the point corresponding to t equal to 0, which would make sense. If t is representing a moving object, then starting at t equals 0 is the obvious thing to do. And so r of 0 is the vector cosine of 0, which is 1, 0 divided by 2, which is 0, and sine of 0, which is 0. So our base point here is going to be given by the vector 1, 0, 0, or the point 1, 0, 0. Right? So now s of t is by definition the integral from 0, all right, our t naught here is 0, to t of the magnitude of r prime of u, du. So the next step would be to compute the magnitude of r prime of u. Now if you look at this function, it might look familiar to you. We actually considered this function in the previous video, and we computed the arc length of this function from 0 to 4 pi. And so in the process of doing that, we observed that this magnitude ended up being the square root of 5 over 2 when you evaluate it. And if you didn't remember that, of course, you can compute it directly. But just to save us some time, since we've already computed this quantity, we're just going to use the fact that this is square root of 5 over 2. And now when we go to do the derivative here, this ends up being just the square root of 5 over 2 times t. Right? We could do square root of 5 over 2 times u, evaluated from t to 0, but that very quickly becomes the square root of 5 over 2 times t. Right, so to summarize this line that we've just computed, we see that s of t is going to be the square root of 5 divided by 2 times t. And so if I wanted to kind of flip this around and solve it for t, I'm just going to multiply both sides by 2 over square root of 5. And so this is also saying that I could think of t as a function of s as 2 times s divided by the square root of 5. Right, and I apologize, my s's and 5's look very similar, so that numerator here is actually 2 times s. It's not 25. Right? And so if the goal is to reparameterize this function in terms of s, what we can do is compute r of, instead of r of t of s. And so we're just going to replace the t with this expression 2s over square root 5. So my arc length parameter parameterization for this function r is going to be the cosine of 2s over square root of 5, s over square root of 5, because we then would have to divide that by 2, and the 2 will cancel out, and sine of 2s over square root 5. Okay, so this is our new parameterization of our helix. And the nice thing about this particular parameterization is that if I take points and I increase s by 1, then each of those points are spaced out on the curve by exactly length 1 on the curve. So if I just take, for example, if I take s to be 0, we get the point 1, 0, 0, which is our base point that we started with. If I then take s to be 1, right, we'll get the point cosine of 2 over square root 5, 2 over square root 5, I'm sorry, 1 over square root 5. This s is 1 here. And sine of 2 over square root 5. And then we take the parameterization with s equal 2. So we're going to get cosine of 4 over square root 5, 2 over square root 5, and then sine of 4 over square root 5. Okay. So we get these 3 points. This is with s equals 0, s equal 1, and s equal 2. These 3 points are all spaced out by exactly 1 unit of distance on the curve. Right? So there's 1 unit of distance on the curve between these points. There's 1 unit of distance between these 2 points on the curve. And so this will allow us to do calculus in terms of the arc length by going along the curve in equal intervals as s increases by the appropriate amount. Typically, this isn't what happens. If we go, in this particular example, from t equals 0 to t equal 1, it might travel a certain distance, but from t equal 1 to t equal 2, the object might travel a different distance. In general, that will happen, but with the arc length parameter, that will never happen. It's really the purpose of the arc length parameter. It's to keep it from, keep the object traveling at a sort of constant speed in terms of this parameter s. Now, as you can probably imagine, this was a very easy example, but in more difficult settings, this parameter might be very, very difficult to find. Notice it involves solving an equation. In this case, it was an easy equation, s equals a constant times t. But that, of course, could be much more difficult based on the integral. And so in a lot of cases, we won't actually need to do what we just did here. We won't actually need to know the arc length parameter in terms of t. It will be actually good enough to know that it exists, and we're going to use it implicitly within calculations. So we just know that this parameterization exists, but we don't always have to find it, which is really good news.